Yeah, no, I was like,
I need to go home.
That's awesome.
I'll drive your house and get your house. Oh, no, I don't show
Zia, you guys can just leave everything there on the back table. Nobody sits back there. It's very Right, so I had a kid ask me outside of the field when I was, Mr. Shelley, you had two vacuum cleaners, you put them right next to each other, you put your head in between both hands, and you feel ready to go.
Hey, who is this girl named Bryn?
No, it's a second. Simplest explanation is usually correct.
just sit in on this.
I know, but you should just like, huh? I'm gonna have a fifth free, and I'm probably gonna have a second free in the first free as well. I'm gonna see if I can switch my gov to second period. I had a friend who did that last time. I'd go surfing all day. I'd have a 4-day weekend sometimes.
Oh my god.
And then whenever we have an actual 3
Not really a 4-day weekend.
Every weekend.
I call it a 3+1.
Okay.
Every weekend. Every week will be a 4-day weekend. Friday.
Hi, Sam.
You're gonna have 4-day weekends every other weekend. You're ridiculous. I have college counselor.
What?
I have college counselor meeting tonight.
No. You don't have time after that?
All night.
Totally got an 8 out of 10 on that. And like, how cute was it? Yeah, oh my god. Yeah.
At least I think.
Yeah. Yeah. It was very
Dog, you're able to get this.
What do you think? Oh, it's not on there. Bob is a great name.
I will be collecting from you the lab report when the bell rings. You have to come here and staple it. Please do so.
Hey.
Roughly in the order that I mean, like your data.
I just don't.
You had
I usually eat very, very small lunches.
It's been planned for a year. Like we've known this date for a year, and all of us.
Do we have to draw?
I'm sorry.
Well, no, we're saying exactly. That's not what I said. Anna, well, no, I keep that to the side of the action. Because I'm not going to start something else.
Oh God, this is like in-depth. That's pretty.
So it's going to be negative 4.9 e squared.
I mean, for me, it's my last year, too.
No, negative 4.9. Because gravity is 9.8 meters per second squared.
He's right about that. I know that for sure.
And then since you have to do a over 2 in the position equation, it would
I actually
be,
don't know what you're talking about right now.
since you have to do a over 2, right? Am I saying that one correctly, sir?
All right, so I am collecting a lab report from you. Please make sure your name is on it, and then please pass it to the right hand side. Go ahead and pass it down, make sure your name is on it, as always. Thank you.
Are you doing this problem already?
Today is
Overachievers.
something.
I know, right?
Today's the 23rd. Is today the equinox? No, not quite. It was actually last night locally at 7:29 p.m. So it was actually Monday the 22nd when it happened here. Now I told you in the past that it was on September 23rd. Why was it last night on September 22nd? Because last night in Los Angeles, September 22nd, it was already the 23rd in prime meridian, 0 degrees longitude in Great Britain, for example. So that's why officially it's the 23rd, even though it typically falls late at night on the 22nd for us here, far in the western hemisphere. Okay? All right, before we begin today, take a look here at the board. Okay, now next time in class is, remember, Friday of this week, and then it'll be school on Thursday. Friday of this week, we'll be finishing up Chapter 2 and reviewing for the next exam. The next exam is on the horizon. It's on Tuesday of next week. It's a week from today. So make a note of that in some manner, and let's go ahead and move on from there. So today we're going to do the following. Today we're going to finish up free fall with a couple of other basic problems just to finish that very important topic. And then we're going to move towards our last topic in Chapter 2, which deals with situations involving non-constant acceleration. You're going to need, however, a mathematical primer on basic calculus in order to understand how we mathematically treat non-constant acceleration. We'll get to that a little bit later on. Now, thus far, I've only done one free fall example in class. I did it at the end of class last time. That was for the simple situation for an object that is dropped from rest. The next basic situation to look at for an object in free fall is an object that is initially thrown upwards, say like so. We're going to look at a couple of basic quantities associated with that. So take a moment here to copy down the problem and just part A. We'll get to the latter parts of the After you've copied down the problem, by the way, also copy down our two basic kinematic expressions, position as a function of time, and also velocity.
What?
So the object is launched vertically upwards from the ground, that's the origin, just to make it easy to picture, with an initial speed of 20 meters per second. First thing that we want to calculate in part A is the maximum height that is reached by the object. This is a problem in metric units, so G is 9.8 meters per second squared. Okay, now here's how we go about setting up part A of the problem. All maximum height problems, as you'll see, are done basically the same way. Okay, we start first of all at the ground, which is our origin. We usually use that for reference in that manner. And so if the object starts at the ground, its initial position, then y naught is equal to 0. And then it's launched upwards, so the initial velocity vector, vy naught, is a positive number. I'll put the plus sign there in parentheses. And then the object will reach its maximum height. And immediately two things are unknown. Its final position relative to the origin, which is the maximum height, and the time necessary for this to occur. Now before we begin the math with the two expressions, even though it doesn't explicitly say so in the problem, for this instant when the marker, for example, reaches its maximum height, what is its velocity?
0.
That's equal to 0. So let's immediately make that note. Final velocity v sub y is 0. Now because the final velocity v sub y is equal to 0, let's begin by taking a look at the velocity equation. In the velocity equation on the left-hand side, v sub y is equal to 0, so I'll simplify that equation in the following way. Notice that the only thing that is unknown in that expression is the time t, which I can then solve for. Once I know what the time t is, then the finished part of the problem, all that we have to do is take that time, along with all the other information, and plug it into the position equation here to find the maximum height. So it's a basic two-step process. So I'm going to solve for t here. I'll do that first by moving the gt to the other side, like so. And then divide by g on both sides now to get the time by itself, and you end up with the following expression. So I'm going to have an enumerator, 20 meters per second, and then divide that by g, 9.8 meters per second squared. Remember, if you just plug in g as a positive number, because a negative sign has already been taken care of in the equations themselves. This comes out to be a little bit more than 2 seconds. It's about 2.04 seconds. So that's the time necessary for the object to go upwards. And then the position, then, its maximum height can be found by just plugging in all the information into the position equation. So we'll have y naught, which is 0, and then 20 times 2.04 minus 1 half times 9.8 times 2.04 squared. So let's then see what we get as the maximum height by plugging in those numbers. So first of all, the middle term, vy naught times t, so 20 times 2.04 minus 1 half times 9.8 times 2.04 squared. Punching all of that out gives us then 20.4 meters. So finding the maximum height here is pretty straightforward. Okay, now let's see in part B of the problem what happens when the object returns back down to the ground. Here's part B. So when it says when and with what velocity does the object hit the ground, it's referring to the last possible instant, once again, that the object is in free fall. Now your mathematical intuition probably pretty quickly is going to tell you the answer. How much time do you suppose is going to be necessary for the object to return back down to the ground? Another 2.04 seconds. You're correct. The time to go up is the same as the time to go down. In addition to that, if the marker leaves my hand moving upwards at 20 meters per second, what do you suppose its velocity is going to be the instant that it returns to my hand? Negative 20 meters per second. Obviously, there's some symmetry here. The reason why there's symmetry is because the position of the object as a function of time is a parabola. And we're looking essentially at the two sides of the parabola about the vertex. We'll show that explicitly at the end of the problem. Okay, now in part B of this example, I'm actually going to do this two different ways. I'll do it two different ways just to illustrate that it really doesn't matter how you set up the problem, as long as you're consistent. If you're consistent from the point that you set it up, then you'll ultimately be able to arrive at the correct answer. So just this one time, to illustrate that here in part B of the problem, I'm going to solve it 2 different ways. Okay, the first method, or first way that I'll solve this, is similar to what you saw me do at the end of class last time. I'm just going to think of the object as starting at 20.4 meters above the ground, and then just dropping from rest all the way back down to the ground. If I think of it like that, then the problem is set up in the following way. So once again, here's the ground for reference. And then we begin with the object here at its initial position, now y0 of 20.4 meters. We're going to think of the object as dropping from rest, so the initial velocity here is equal to 0. And then it falls all the way down to the ground in an unknown amount of time t, and it will have an unknown final velocity v sub y. When it does return to the ground, its final position, by the way, y is equal to 0. So this is very similar to what you saw me do at the end of class last time, in just dropping an object down to the ground. Okay, now in this case, because both the final position and the initial velocity are 0, let's begin by taking a look at the position equation. In the position equation, 2 things are 0. Final position y and the initial velocity vy0. So this position equation then simplifies to become this. So notice that I plugged into the expression above 2 things that are equal to 0, thereby arriving at this point here. And now all that I'm going to do is solve for t. When I run through the algebra here and solve for t, I'm not going to quite get the same equation as this. Up here in red, this came from the velocity equation. Here in green on the bottom board, this is the position equation. But from symmetry, I should get the same number. Let's see if I do. So I'm going to move the 1/2 gt squared to the other side. So, cross multiply by the 2 and the g, and then take the square root. So when you do those couple of minor algebraic steps, summarizing them at once, we arrive here. And at this point, we just plug in the numbers. So I have the square root then of the quantity, 2 times 20.4 in the numerator, then divide by g, take the square root of all of that. Sure enough, of course, it's the same time, 2.14 seconds. So time to go up is the same as the time to come back down. Makes sense. Okay, then similarly, we can find the final velocity. To find the final velocity, we'll use the velocity equation, where right here, remember, we're dropping the object from rest, so the initial velocity is equal to 0. So that velocity equation then just becomes minus gt. So I take the time that I have here of 2.04 seconds, just multiply by g. The negative sign, of course, indicates that the object is going downward. And yes, sure enough, the speed is also 20 meters per second. So the marker leaves my hand at 20 meters per second and returns to the hand at 20 meters per second. Now, solving the problem as you saw me do here was fairly simple and straightforward, but there's another way in which I can do the problem. I'll illustrate that second method just to show once again that it really doesn't matter how you set up a problem. As long as you're consistent, you'll be able to arrive at the answer. Sean, I'm sorry, your question.
So correct me if I'm wrong, but when you say you throw an object up in the air, right? The force that you exert.
Oh, I haven't said the F word yet. We'll get to the F word a little bit later on.
I'll skip the F.
Okay.
Well,
Let's think of it this way. As I've gone through this chapter and also into the next chapter when we talk about 2-dimensional types of motion, I haven't said a word as of yet about what causes all of this. The kinematics is the mathematical description of motion. Right now we're just describing an object in free fall. Why this happens, that's dynamics. That'll be chapters 4, 5, and 6. So for now, I'm just making sure that you guys understand how we deal with mathematically describing motion,
Right.
which is basically just position, velocity, and acceleration.
Okay.
What causes all of this, we're still getting to.
But how would the velocity be the same about and how would it like how would the gravity be the same?
Okay, so why is the velocity, why is the speed, to be a little bit more precise, why is the speed the same going up and going down? Because it has to do with something called conservation of energy, which we'll get to a little bit later on in this semester. I know you guys already have a basic familiarity with it, but we're actually going to lay out the nuts and bolts of exactly how energy transfer works when we eventually get to chapters 7 and 8. So you're once again looking a little bit ahead in the course by asking a question such as that. Okay? But yes, I will eventually answer your question. It'll just take me some time. Okay, now just finishing up here once again with part B. This is the second method, as I mentioned. It's perfectly valid for me to think of part B in the following way. what I'll do in this particular case is start the object at the ground again, like so. So its initial position, y naught is equal to 0, and I'll throw it upwards. V y naught once again, up plus 20 meters per second. But then I'm going to think of the final position in this problem as the same. That is when it returns to my hand, for example. So I'm going to think of the object's final position, y, as also being equal to 0. And then two things here will be unknown. Time t, and final velocity, v sub y. So it's perfectly valid for me to think of the problem like that. Start when the marker leaves my hand, and then end when the marker returns to my hand. Now, if I think of the problem like that, how do I go about mathematically treating it? Well, we note immediately here that both the final position and initial positions are 0. So if both y and y naught are 0, that then means that my position equation is going to simplify. We'll have this term here as 0, as is this term here. So that expression then becomes this. So take a look at that. I said both y and y naught equal to 0. And if you do look at the expression carefully, what is the only unknown that is there? It's the time t, so I can solve for it. But be careful. Technically, it's a quadratic, so there are two answers. Notice that one of the answers is simply 0. 0 minus 0 is equal to 0, and it makes sense because the object is here at the origin at time 0. Okay, we don't really care about that time, however. We want to find the other value. So to find the other value of t here, because the left-hand side of this expression is equal to 0, I can just safely cancel out a t from each term like so, and now just solve for the one that remains over here. So take this 1/2 gt and move it to the other side. Oops, 1/2 gt. And that then equals just vy naught here, remaining on the right-hand side of the expression. And then lastly, just cross-multiply by the 2 and the g here, and when you do, you arrive at this expression here for the time. Hang on a second, Zach. Before I plug in my numbers, notice how that time here, basically to go up and down, is related to this time here, which was just the time to go up. How is that quantity related to this one? It's just double, it's twice as much. So in other words, what we calculated here was the total time that the object is in free fall, 4.08 seconds. So, okay, before I lastly get the final velocity with this second method, Zach, you had a question?
Yeah, so why can you just cancel out those two?
Okay, I can do that because if I take 0 and divide it by t, I still get 0. So in other words, all I'm doing here is just dividing each term by t. That's an easy way to do the
Oh,
algebra.
you're just dividing.
Yeah, I'm just dividing the whole thing by t. And I can do that because I know that the solution I'm dividing out is t is equal to 0, which is what happens when the object begins the problem. We don't care about that time, however. We know on the other one, that's this right here. Of course, the meaning of this time here in the context of the example means the same thing as this. Okay, then lastly here for this second method, we can find the final velocity v sub y by now just plugging everything into our velocity equation. We'll have 20 minus 9.8 times 4.08 seconds. So punching that out, 20 minus 9.8 times 4.08, and sure enough, it's once again negative 20 meters per second. So it doesn't matter which way you set up the problem, you'll still arrive at the correct answer if you do the process correctly itself. But sometimes with a little bit of practice, we may notice that one example or one method may be a little bit easier than another. That, however, just takes a little bit of experience, okay? And then lastly for this problem, let's take a look briefly at a part C. Let's kind of examine an in-between position, if you will, for the example. Let's take a look at this. Okay, now it's asking us for basically two things when the position is 5 meters. Notice that 5 meters, of course, is less than the object's maximum height in part A of the problem, which was 20.4 meters. It's asking us, first of all, the time or times when this happens. How many times will the object be at a height of 5 meters? Twice, once on the way up and once on the way down. And then we're also asked to calculate the velocity. What should be the same, do you suppose, about the velocities, yet different? What do you think? One will be negative, the other will be positive, and they will be, in fact, the same speed. This also has to do with conservation of energy, to answer your pending question. Well, we'll get to that a little bit later on. But for now, just to describe it, that's all that we're doing there. Think of part C in the following way. Once again, we'll take the object and launch it from the ground. So y naught is equal to 0, and vy naught, once again, is our positive 20 meters per second. And now the object doesn't reach its maximum height, it reaches just specifically this height here, its final position y in part C of the problem, is 5 meters. And then what's unknown is the time or times when this happens and the velocity, v sub y going up and v sub y going down. So in terms of a basic drawing, that's how I would think of it when it's here at this position. Okay, now because we are given specifically the position as 5 meters, let's just begin by looking at our position equation where the left-hand side here is 5 meters and the y naught is equal to 0. So if I just briefly rewrite that expression, excuse me, and this, and if you look at the expression carefully, what is the only unknown? And it's a time t. I'll be able to solve for it. There will be two answers, but now you got to be careful here. This is not 0, this is 5. So then therefore, what am I going to have to use to solve for my two times here? Yes, quadratic formula. So who would have thought that quadratic formula is contained in this? Now to see the quadratic formula here in this example, let me take these two terms here and here and move them to the left-hand side. So if I move them over to the left-hand side of the expression, I'll obtain this. Like so. And now using the coefficients a, b, and c, like you do when you learn quadratic formula, we would have to think of those coefficients in the following way. Okay, right here is the quadratic term. The 1/2 g here is the coefficient a. And then in front of the linear term here, including the negative sign, the negative vy naught is our coefficient b. And then we have the constant here, y equal to 5 meters. That right there is our coefficient c. And now we just set up the quadratic formula. So I know it may have been a while, but remember how the quadratic formula goes. We're going to first of all have negative b. So the negative of negative vy naught is positive vy naught. Plus or minus, so yes, two answers. Square root of b squared. Now when I square the b here, the negative sign is just going to square out. So I get vy naught squared. Then minus 4 times a times c, and then all over 2a. Like so. So in terms of my coefficients, this is what the quadratic formula is going to look like. It will simplify for us a little bit in just a moment prior to actually plugging in the numbers. Okay, to simplify, notice in the denominator, first of all, that the 2's cancel out here and here. And then up underneath the radical sign, I can cancel the 2 here and here, thereby bringing the 2 up front. And now I just start plugging in my numbers. I'll write this out as I go for simplicity. Okay, so first of all, I have right here 20. And then plus or minus, I'll do the radical sign here on my calculator. I'm going to have 20 squared first of all, which is 400. Then minus 2 times g times 5 meters for y. Take the square root of all of that junk, and I end up with about 17.4. And then divide by just g in the denominator after I cancel those 2's, 9.8. Now when I use the negative sign here in the numerator of the expression, this will give me the lesser time on the way up. So 20 minus 17.4 and then over 9.8. And rounding it off a little bit, it comes out to be about, let me check that, 20 minus 17.4. Comes out to be about 0.27 or so seconds. Okay, then using a plus sign there in the numerator will give you the ladder time. This should be on the way down. So 20 plus 17.4 and then all over 9.8. Once again, rounding it off a little bit, that's about 3.82 seconds. So time on the way up and time on the way down. And then lastly, then we can calculate the final velocities by just taking those two times and then plugging them into the velocity equation where the Vy naught, remember, was 20 meters per second. So calculating V sub y would be first of all calculated for the 0.27 seconds. This is the lesser time, so this should be a positive velocity when the object is on the way up. Let's see if it is. So going up to my velocity equation, 20 minus 9.8 times 0.27, that comes out to be positive 17.4 meters per second. Watch what happens with the ladder time. It'll be 20 minus 9.8 times 3.82. That comes out to be negative 17.4 meters per second. Notice that that number, by the way, is the same as this number. That's not a coincidence. The reason for that is because this number here, which is this radical sign, it's the third kinematics equation. I haven't used it explicitly in this example. But remember what the third kinematics equation for free fall looks like. It's this expression here. Notice that the right-hand side of the equation, if you take the square root of it, is underneath the radical sign. So if I'm taking the square root of this, I end up with plus and minus v sub y. In this case, it's the number 17.4 meters per second. So it's not a coincidence, it's just how the math works when we combine things together here in algebraic. You know, obviously, throughout this basic example, there's been lots of symmetry that's been hinted at. Seeing the symmetry here is very easy to do if you just quickly sketch out for this example a couple of simple graphs. For example, if for this example I graphed velocity as a function of time, we then simply have the following. When we graph velocity as a function of time for an object in free fall, it's always the same line. It's always a line with a slope of minus g. In this particular case, however, the initial velocity, the y-intercept, was positive 20 meters per second. So then therefore, our line for this problem basically looks like this. And right here was 20 meters per second. Down here was negative 20 meters per second. And then our times were as follows. Right here was when the velocity was equal to 0 for an instant. That's when the object was at its maximum height. This was the 2.04 seconds that we calculated in part A. And then after another 2.04 seconds for a total of 4.08, the object would turn back down to the ground with a velocity of negative 20 meters per second. So right there is basically parts A and B of the problem on the velocity graph. And then part C of the problem was the following. Right here was a velocity of 17.4 meters per second. That then right there was 0.27 seconds in terms of the time. And then right here was approximately negative 17.4 meters per second. Right over here in terms of the time in blue, that was 3.82 seconds. Like so. So that's basically what part C looks like on the graph as well. The left-hand side and the right-hand side are essentially the same, just by symmetry. We could also see the symmetry for the position as a function of time as well. It's very easy to describe in this problem. That would just look like this. So position as a function of time for an object in free fall is always the same parabola that moves downwards. For the object that is thrown upwards, as we're doing in this example, the vertex of the parabola is just in the first quadrant. So the parabola itself just looks like this. Okay, now this right here was the maximum height from part A of the example. That was 20.4 meters like so. And then we had the following times. This time right here, the maximum height was 2.04 seconds. This time over here was 4.08 seconds. so. Once again, obvious symmetry. Okay, and then lastly was essentially part C of the problem. Right here, we have a position of 5 meters. This point right here, 0.27 seconds. And then on the other side of the vertex, like so, this point here in blue is 3.82 seconds. Okay? So yeah, essentially everything that's happening while it's going up is the same as while it's going down. We're basically looking at the 2 halves of this position graph, or equivalently, the 2 halves here in this velocity graph. Okay? Any questions thus far? Here you go. Let's finish up free fall with just one more basic example. Let's do once again a little bit of rocket science. I'll try to throw some rocket science at you guys as well. Now, as you begin to read through this example, we're going to note a couple of things. The first thing to note right off the bat is that it's in English units. Notice that that acceleration that's described there is in terms of feet per second squared. So when we eventually do describe this rocket in free fall, we have to set g not equal to 9.8 meters per second squared, but 32 feet per second squared. That's its equivalent value in the English unit system. Notice for the first 60 seconds of the problem while the rocket's engine is firing, it's not in free fall. It's accelerating upwards at 64 feet per second squared. What causes all of that, we'll get to a little bit later on, but for now it's just accelerating upwards for 60 seconds at 64 feet per second squared. And then afterwards the engine shuts off. Part A of the problem, we want to calculate the maximum height that's reached, and then eventually in part B of the problem we want to describe what happens when the rocket just returns to the ground. Now, if you're having a little bit of trouble visualizing this, it's really just nothing more than the following situation. So imagine that this pad of paper here is the rocket itself, and then while the engine is firing, that's basically what's happening while it's in my hand, and I accelerate it upwards. So right now it just begins to rest here on the launch pad, and then the entire problem is literally just this, like so. So while it's in my hand, that's when it's accelerating upwards at 64 feet per second squared. But then after I let go of it, then it's in free fall for the remainder of the problem. So what I need to calculate after the first 60 seconds are 2 things. I need to find the position and velocity of the rocket the instant that the engine shuts off. The reason why I need that stuff is because I need to know basically what's happening the instant that I let go of the pad of paper, such that it then continues in free fall. So I need those values in order to do part A of the problem. So in other words, I have to break the problem up, obviously, into a couple of parts. Let's look to see what happens first of all while the engine fires. It does so for a time here t of 60 seconds. So how would I begin to think of this? Well, here's the ground once again as my origin. The rocket here begins on the ground, on the launch pad, if you will, initially at rest. So its initial position, y0 is equal to 0, as is its initial velocity, v1. That's also equal to 0. But then it accelerates upwards. It accelerates upwards in the y direction. So I'll refer to that acceleration as a sub y, and that's 64 feet per second squared. And then after 60 seconds and the engine shuts off, then the rocket looks like this. It's up here somewhere like so, and there are 2 things that are unknown about it. We don't know its final position y relative to the origin, nor do we know its final velocity v sub y. I need to find those 2 values, because once I know those values, then I'll be able to describe what happens after the rocket continues in free fall, when we eventually do, in fact, hit the part A of the problem. Now, don't be fooled here. This is still just one-dimensional motion with constant acceleration. It's like a car starting at rest, for example, and just speeding up as it goes. One of the problems that we looked at, for example, early on in the chapter. However, this is all still taking place vertically. So I'm going to write down my equations in terms of the y direction. Think of the equations, then therefore, like this. You notice how I'm writing this position equation. It's essentially the same thing as we saw earlier in the chapter as x equals x naught plus v naught t plus 1/2 at squared. It's the exact same expression, now just written out vertically. Okay, same thing for the velocity equation, just written out vertically. It looks like this. Once again, earlier in the chapter, we saw it as v equals v naught plus at. It's the exact same expression, just written out in the vertical direction. Now, these two equations here simplify dramatically in this problem. Take a look at the position equation first. Two things are equal to 0. The initial position of the rocket, and it begins at rest. So this position equation simplifies immediately to become the following. Now notice that there's no additional algebra to do here or anything like that. All that I do have to do is just plug in these numbers, and I can then, in feet, get the height that the rocket is when the engine shuts off. So let me go ahead and find that immediately. It's just 1/2 times 64 feet per second squared, multiplied then by the time of 60 seconds squared. This comes out to be 115,200 feet. So that's its altitude above the ground, if you will, when the rocket engine shuts off. Okay, let's find its velocity when the rocket engine shuts off. That's from this expression here, which also simplifies, by the way, because the rocket begins at rest. So because the rocket begins at rest, my velocity equation just becomes acceleration times time. So 64 feet per second squared, multiplied by the time of 60 seconds, then gives me 3,840 feet per second. So I now know what happens to the rocket when the engine shuts off, and now we can do the remainder of the problem. So now, strictly speaking, we get to part A, when the object is in free fall. So because the object is in free fall, now I switch back to my free fall expressions once again. Like so. But you have to be a little bit careful in this example because of the English units, as I said. So we have to write G. It's not 9.8 meters per second squared, but it's equivalent in the English system, which is 32 feet per second squared. Okay, now part A of this problem, by the way, is just another maximum height example. It's a little bit different than the one that I did earlier today, but we set it up, however, in much the same way. Think of now part A like this. So here's the ground, but remember that the rocket doesn't begin in free fall at the ground. It's up here. It's already at a height. Now its initial position, y naught, 115,200 feet. And it begins with a velocity upwards, Vy naught, of 3,840 feet per second that I found a few minutes ago. But then when it reaches its maximum height, for an instant, it ends up here at rest. So its final velocity v sub y here for an instant is equal to 0. And then there are two things that are unknown. Its maximum height reached, which is the magnitude of this final position vector y, and the time necessary to go from here to here on the diagram. As I said earlier, maximum height problems always begin much the same way. Because the final velocity v sub y is equal to 0, mathematically we begin our analysis of the problem with the velocity equation. So in the velocity equation, set the v sub y equal to 0. So, and now I can just go ahead and find that time. Once I have that time, along with all the other information, I will then plug that information into the position equation here to find the maximum height. So maximum height problems are always done the same way. So move the GT to the other side and do the algebra here. So, divide by G on both sides to get the time. And now I punch in my numbers. Just be careful of G. Remember, it's 32 feet per second squared. So the numerator of the expression is 3840 feet per second, divided by G of 32. And it actually continues upwards, by the way, for a full 2 minutes after the engine shuts off. So the engine was firing for a minute, and then when you shut off the engine, the marker, the rocket, continued upward for an additional 2 minutes. Okay, now that I know that time, and that's, by the way, the time, remember, from here to here, I now find the magnitude here of the final position vector by just plugging everything into the position equation. When I do, though, you gotta be careful. The y naught here, remember, is 115, 200 feet. So I'll have 115, 200 feet first, 5, 200, plus then 3840 times 120 minus 1/2 times 32 times 120 squared. So after all of that, the final altitude, if you will, above the ground that the rocket reaches is 345,600 feet. So that's pretty high up. Exactly how high up is that? Well, you guys know how many English feet there are in a mile?
5,200.
5,280. So let's see, divide by 5280 feet per mile. That's about 65.5 miles. 65.5 miles above our heads. That's about the point where the atmosphere is thinned out to a vacuum. So that's pretty much outer space at that point. Outer space is basically about 65 miles or so above our heads. So if you take the rocket and throw it upwards, as we're doing here in this problem, it will basically reach the edge of space.
Drive my car an hour.
Yes, if you wanted to drive your car for an hour straight up at 65 kilometers per hour, you would drive into space. I'll leave it to you to go ahead and build a road that does such a thing. You can engineer that for us. Okay, now, if you take this rocket and throw it straight up as we're doing here in part A of the problem, what's eventually going to happen to it? It's just going to fall straight back down again. How an object ends up in orbit, we'll get to that a little bit later on. But for now, if you just take a rocket and throw it straight up, boom, it's going to fall straight back down again. So lastly, let's see what happens when it does. You probably don't want to be standing underneath. Maybe for extra credit. I got it. Okay, now let's just think of part B as just dropping the object from rest again. It's usually the easiest way to do a problem such as part B. So in this particular case, I'll set it up in the following way. So once again, here's the ground for reference. Here's a rocket like so to begin the problem. Now its initial position here above the ground, y naught, is the 345,600 feet that we calculated a few minutes ago. Okay, it begins at rest. Y naught is equal to 0. Then we just drop it all the way back down to the ground again. So when we drop it back down to the ground, its final position y is equal to 0, and then two things are unknown. Time necessary to fall back down to the ground, and the final velocity v sub y. Is the final time here to fall back down to the ground just simply going to be 1 minute plus 2 minutes for a total of 3 minutes? Is it just going to take 3 minutes to fall back down to the ground again? No, because remember that it's not in free fall here in the top core while the engine fires. This is like a different parabola with a different acceleration than this one here when the object is in free fall. So don't automatically assume some sort of symmetry here in this portion of the problem as opposed to what we saw earlier, because you have to remember that for a portion of the problem earlier, the object was not in free fall. But finding that time mathematically is really easy to do. Here's how we go about doing it. So we look at our position equation for free fall, and we set y equal to 0 and vy naught equal to 0, like I did in an earlier example. So, and then from that expression, we can just solve for the time. So after we do the necessary algebra by moving 1/2 gt squared to the other side, cross multiplying, etc., after you do those couple of minor steps, like in the previous example that I did earlier today, you end up with this equation here. Okay, now let me go ahead and punch in my numbers here. This time is going to be a little bit long. 2 times 345, 600. I'll divide by 32 for g. Take the square root. And that comes out to be about 147 seconds. So it takes about 2.5 minutes to fall all the way back down to the ground after reaching an altitude of about 65 miles. So the total amount of time from launch to impact is about 5.5 minutes. So we fire the engine for a minute, moves upwards for an additional 2 minutes, and then takes about 2.5 minutes to fall all the way back down to the ground again. And once I have that time, lastly, using the velocity equation where v y naught is equal to 0, we find this final velocity v sub y. As I said, you probably don't want to be standing underneath this. So let's see how fast it's moving. So 32 for g times 147, this comes out to be about negative 47.4 feet per second. So that's nearly a mile per second. A mile per second would be 5,280 feet per second. This is pretty close to it. So as I said, you don't want to be standing underneath. Yeah. Nice little problem for free fall. Any questions? Okay, let's take a short break. I'm sorry? Sure, you can do it. Why don't you use the side gun? Sure.
I looked back, but you were working out. You really have to go to the
No, no. You have to think of the top board as being completely separate from that bottom board. So that does not create 6. Well, it's whole, yes, when you add the two times together. You have to think of the times as separate.
We have to sit here, right? That one was long, that was longer.
And
But like, I need to sit and memorize all like. I'm a big over here.
oh, what is that? That's not being.
I'm gonna start my homework. I like that.
Yeah, it's not being over here.
I'm gonna do next year too.
I suggested it, so you can do it.
Who's drawing these stars?
That was hard.
I already crashed.
Using what I have. We use another formula.
No, I don't.
Yeah, depending on the equation, like if certain that makes the beginning set equal to 0. And then if it's gonna end up back on the ground, then it's gonna equal to 0 again. What?
There's something on the podcast.
What?
And then on Friday, and then I was gonna go out on Saturday, but I was like, no, I'm gonna get art done. I didn't get any art done.
What art?
I'm like 3 projects behind, casually, but still haven't been doing it.
Like AP art? For seniors?
All of you?
Yeah. Don't even start.
It's the only thing we talk about ever.
Sucks
Like, I don't even have any other thought, like, there's a constant,
It sucks. I'm totally pushing it off.
do like 4 like college essays.
4? I'm gonna use one of the. I'm gonna use my Common App for my presentation.
yes. You're not using one of your things.
for Northwestern.
There's like a million different
Supplement, MIT's application sucks.
You're applying to MIT?
Yeah, but just for fun. I'm gonna do it
Just
for
for
fun.
fun?
Those apps are so fun.
You're gonna get into college.
Yeah.
So there's
So
another
we're
one.
gonna-
What do you want to do?
Did you already apply to this?
No, I'm applying. It starts Wednesday. I'm skipping second period just over to
Excited.
Why would you skip surf?
architecture.
It's a really hard program.
Because
It's the number 1 undergrad. Right, it's number 1 undergrad in the country.
Caltech.
Yeah, but you're
Yeah,
getting into Caltech.
But Cal Poly is a good, really good
California is
school.
also really
No,
hard
no,
to
you
get
gotta stay with me,
for
come on.
It's
It's number
See, that's the
1
problem with fire drills,
undergrad
everybody goes out to the field, and then afterwards they're all like this.
You can check the system by applying for art science, switching.
They make it
No,
incredibly
I know.
difficult.
I went
That's why
there, and they said it's hard,
But it might be easier for you to MIT because you don't have enough girls.
Yeah, no, I know.
Are you serious?
Honestly,
Is that an actual thing?
Yeah, actually, colleges try and make their
No, and
campuses
also, like,
very.
I just
No, I know that, but I'm talking
my,
about
But
MIT.
MIT, what's like the,
talking about
I'm not sure, I just know compared to Center of Girls is really small.
just go to
I wanna go to school.
In where? You wanna go to school in all boys?
So you wanna go to all boys?
No, I'm kidding, I'm just like, I'm not, I don't wanna be in a sorority, like, I don't wanna deal with like the girl.
But you don't have to be in a
so
sorority.
catty.
I know, but
No, you don't have to.
All right, everybody, please take your seats.
Where'd it go?
So we now get towards the last section of chapter 2. Last section of chapter 2 is a brief introduction of how we mathematically deal with situations involving non-constant acceleration. Now, earlier in the chapter, when I started to describe constant acceleration, I mentioned that it's the simplest type of motion to describe because it's the only type of motion that you can describe algebraically. All other types of motion involving a non-constant acceleration, you have to use the methods of calculus in order to go through that description. So here what I do at this point in chapter 2 is I give everybody a brief primer on how to find derivatives and how to integrate just polynomials. I do expect everybody in honors physics at the end of this process to understand how you differentiate, that is, find derivatives, and integrate simple polynomials. For some of this, for some of you probably, this will be a review, and that's perfectly fine. Now, as I go through how you take derivatives and how you integrate polynomials, we are only concerned with, in this class, method. I'm just going to go through the methods that we use of doing this process, the processes. I'm going to skip over the theory that's behind of what I'm about to do. The reason for that is because you're going to get the theory anyway in your calculus class. I'm just going to skip over that portion of it. We're just concerned here with method. Okay, first of all, derivatives. It turns out that exactly what is meant by a derivative and finding derivatives for polynomials is actually pretty simple and straightforward. Now, as I describe this, I'm going to do so purely in terms of mathematical terms. So I'm going to try to use the exact same notation that you will see in a calculus class. So for example, let's say that we have a function of x, and it's some smooth curve polynomial, like so. And then we just take a look at two values along the x-axis. We look at right here, a value that's just specifically labeled as x. And then we look at a second value right here that is at a greater number. This greater number here, using the mathematical notation, is usually referred to as x plus h. So the h is just a distance here on the axis itself. It's the difference between these two values. Okay, now, the function itself has some value at this discrete value of x. The value of the function itself is just f of x right there at that location. And then right over here at this separate location where the value of x is x plus h, the function has a different value over here, f of x plus h. And then what I'm going to do is, like you saw me do earlier when I was describing motion, is connect the 2 points with a chord and find the slope of that chord. So here are my 2 points like so. Connecting the 2 points with a chord gives me this line right here. So, the slope of that line, the slope of the chord, is an average calculation. It's describing to me how this red function is changing as we go from here to here. So the slope of the chord is just equal to rise over run. Well, the rise is the difference between these red values right here of the function. The greater value minus the lesser value. And then the run is just the distance between these 2 points right here, which is just this distance h here on the diagram, like so. So that's, once again, just rise over run. It's just the slope of the line that connects the 2 points. But as we've already have seen with motion, what we are more interested in is coming up with a complete description of how exactly the red function is changing right here at this discrete value of x. In order to do that, I have to find the slope of a line that is tangent to the curve at this location. That involves taking the value of h and shrinking it down to 0 size. So in terms of a graph, like you've already seen, this. mathematical notation. Here's my red polynomial smooth curve of some sort. Right here is this discrete value of x. So to know exactly how my red function is changing right there, at that discrete value of x, technically what I'm finding is the slope of this line that is tangent to the curve right there at that location. It's the same thing as the quantity above, except we've now taken an h here in the denominator, and we've shrunk it down to 0 size. Okay, this quantity right here, the slope of the tangent line, the derivative, is written out in the following way. Okay, first of all, some notation. You're going to see it written as f prime of x, typically in a calculus class. This refers to the derivative itself. In a physics class, such as what you've already seen, the equivalent notation would be the following. But regardless, it's the same thing as I've described up on the top board. It's just that we've now taken the denominator, the run, if you will, and have shrunk it down to 0 size. And then at this point, this is where the theory would come into play in the calculus class. You would be introduced to what is called the first fundamental theorem of calculus. Essentially, the punchline of that theorem is just this. When you evaluate a derivative, you do every possible mathematical operation that you can do first. And then once you've done that process, then you can take the value of h and shrink it down to 0 size. That's essentially what the gist, if you will, of the first fundamental theorem of calculus is. So then as a process, finding derivatives using this for polynomials is really easy to do. And after I do this process for a couple of really simple polynomials, there's a very simple pattern that emerges. Now let me apply this to a couple of simple examples. Okay, let's say that first of all, the function is a constant. Now before I even calculate the derivative, visualizing what it is actually really easy. Think of it like so. Now if you graph out a function that's a constant, it's of course just a horizontal line, like this, and a value of c. And remember essentially that what a derivative is describing is the slope of a tangent line. What is the slope of a tangent line right here if the function itself is a constant? 0. Yeah, it's equal to 0. So the derivative should just be equal to 0. Here's how you show that explicitly with this quantity. Limit, h goes to 0 of the following. Okay, what we have are two values of the function. The function at a greater value of x, equals h, minus the function at a lesser value of x, f of x. The function itself, in this case, is a constant. So it's just nothing more than c minus c. Divided by h. Once again, here's where the theory comes in. What the theory allows you to do, essentially, is you do all mathematical operations first. And then once you've done that process, then at the very end, you shrink h down to 0 size. Now when I apply that as a process to this example, in the numerator of the expression, c minus c is just equal to 0. And I just then, therefore, end up with 0. Now technically what I'm actually doing here is I'm taking 0 and I'm dividing it by an infinitesimally small number. 0 divided by an infinitesimally small number is still 0. So that's why the derivative in this case is equal to 0. Okay, what about some other simple polynomials? Just say a line and a parabola. Well, if the function is linear, once again, seeing how the derivative works is straightforward. Let me write the function itself. It's just cx. And then if I was to graph this line here, with the slope of c, so, notice that the derivative should be a constant. In other words, the slope of the line here, tangent to the curve, the slope of the ruler's edge, should always just be the same thing. It should just be equal to c. Let's see if it is. Now when we write out the derivative here, by the way, it's usually the first step that trips up introductory students. How do you deal with this term right here? All that you do is you take in the function itself your value of x and just replace it with an x plus h. So if I replace the x here with an x plus h, I just get this as this term. And then minus f of x, which is just cx, and then divided by h. And when you get to this step here then, once again, what you do mathematically is every possible mathematical step that you can do, and then finally at the end of the process you plug in h as 0. So what I want to do is simplify that numerator. So to simplify the numerator, I'll just distribute the terms. So I have cx plus ch minus cx over h. Notice how this immediately simplifies. Positive cx and negative cx cancel out, like so. And then with the terms that remain, notice that I can cancel out an h from each term. And all that I'm left with then is the constant c. Like so. So the derivative of a line is a constant. The slope of the line tangent to the curve never changes. Amanda, do you have a question?
And just on like examples and stuff, do you want us to show this work or can we
I'm
just-
doing it as a two-step process, okay? I'm aware that a lot of you are already familiar with this from calculus, but some of you may not be. But there is a very simple pattern that emerges. I'll do one more example before I get to the pattern itself. The pattern is called power law, those of you that remember it. Okay, now the other example that I'll do just to finish is a parabola. So just keeping the parabola easy. Let's just think of it as a cx squared. Okay, before I actually calculate the derivative, understanding what it has to look like is fairly straightforward. If I graphed my function here, parabola with the vertex at the origin, it would just look like this. And notice that mathematically, the derivative has to behave in the following way. Right here at the location of the vertex, the slope of the tangent line there is 0. But watch what happens to the slope of the tangent line as x increases. The slope of the tangent line gets bigger and bigger and bigger. So when I calculate the derivative, I should end up with a function where its value gets bigger and bigger and bigger as x gets bigger and bigger. Let's see if that happens. So then here's how we approach it. Once again, as I said, it's usually the first step here that trips up students. What you have to do is take the function and replace the x with an x plus h. You have to write it like this. And then minus the function itself, and divided by h, like so. And then you do your math, and you simplify this as far as you can possibly go. So now to do my math here, what I have to do is I have to FOIL this thing, multiply the terms by c. I'll do all that stuff for us. Once you do, you end up with this. And then minus the cx squared over there to the right. Divided by h. So let me just double check myself while you're writing it down. X times x times h, plus another x times h times h, all multiplied by c. Looks good. And now we simplify this, as I said, as far as it can go. So the cx squared here and the negative cx squared cancel out, like so. And then with all the terms that remain, notice that I can cancel an h from each term. So here, here, and here. Now if I just kind of clean up what's left, before I do finally now take my limit, we have 2cx in this term, and plus ch. And now I can safely let h shrink down to 0 size, thereby arriving at this function here. Notice that that's a line. What that line is describing is the slope of the tangent line, the slope of the marker's edge here, for example, as we increase the value of x. The slope of the marker's edge here is actually increasing linearly as x increases on that graph. That's basically what this describes. Okay, now as I said, there's a simple pattern that emerges when you do this process for different polynomials. This pattern is sometimes referred to as power rule. Employing power rule is really easy. Here's how it works. Take a moment to copy this down, and what I'll do is I'll apply it to two of my little examples. So how does this work? Well, think of my line example from a few minutes ago. Well, let me explicitly write it like this, just so we can see the exponent. Just as a simple shortcut, just as a simple process, without actually going through a proof of this. Here's how you find the derivative. What you do is you take the value of the exponent and you bring it down in front, like so. And then you take the value of the exponent and you lower it by 1, like so. And now if you clean this up a little bit, what is just simply equal to? Well, it's just equal to c, like so, which was the derivative from earlier. So as a process, doing this is really easy for polynomials. It doesn't matter, by the way, if the value of n is a positive number, or a negative number, or 0, or a fraction, or a decimal, or whatever. It doesn't matter. It always works in this manner for polynomials. Okay, watch this occur for my second example, or a little earlier rather, the parabola. Cx squared. So to find the derivative here, using this rule, you just take the exponent and bring it down in front, and then take the value of the exponent and lower it by 1. 2 minus 1 is equal to 1. This cleans up a little bit. It's 2cx. So using the power rule, as it's called, this pattern to find derivatives is easy. There's nothing to it. This is basically, by the way, what you'll learn in the first semester of a calculus class. You get all of the theory that allows you to do all of this stuff, and then you basically spend the rest of the semester practicing on how to apply various rules of differentiation to different types of functions. That's basically the first half of introductory calculus. And then the second half, the second semester of introductory calculus, is integration. Integration turns out to be the reverse process of differentiation. Conceptually, however, it's a little trickier to understand, but here's the basic idea. So yes, I'm cramming 2 semesters of calculus into about a half an hour. No, I don't want to teach calculus. No thanks. Let's just use it. Okay, so integration. Integration, as I say, conceptually is a little trickier. Derivatives is fairly straightforward. Integration. Okay, strictly speaking, what integration is concerned with is finding areas under curves. Here's what I mean by that. I'm going to use here the exact same notation that you would see in introductory calculus. And once again, let's say that I have some smooth curve polynomial, like so. And then I have 2 points along the x-axis again, but they're named a little bit differently in this context from what you saw earlier with derivatives. We call this lesser value here a, and we call this greater value here b. Now notice immediately that because of the curvature of this function, whatever it happens to be, I can't use simple geometrical tricks in order to find this area here underneath the curve. The ancient Greeks themselves tried to come up with various geometrical means of finding the true area underneath the curve, and they actually could never do it. But how we do find the true area underneath the curve does in fact begin geometrically. What we do is we start by making an estimate. The estimate is done by dividing up this area underneath the curve here into a series of rectangles. And all of those rectangles have the same width, to keep it simple. Think of it like this. So here's a rectangle like so. Here's a rectangle. Here's a rectangle. People are whispering something called Riemann summation. so on, and so on, and so on, and so on. And now let's just look at one of those rectangles and describe its area. Okay, the area in question of this rectangle, the rectangle itself, by the way, is referred to with the index, a letter K. It would just be base times height. Now the base of this rectangle, this kth rectangle here, is just delta x, and it's the same for everybody. And then the height of this rectangle, like so, is just the value of the red function right here at whatever this value of x happens to be. This value of x right here is just referred to as x sub k, corresponding to the kth rectangle. Now the area of that one rectangle is just the following. It's just equal to its height multiplied by its base. So finding the area of that one rectangle is simple. I can also very easily find the area of all of the rectangles by just adding them all together. Add over the k rectangles. So k equals 1, k equals 2, k equals 3, k equals 4, 5, and so on. Just add them all together. So the area of all of the rectangles would be equal to this. You sum over the k rectangles of all of their heights multiplied by their bases. So that gives me this is just geometry, geometrically. It just gives you the area of all of those rectangles. But is it the true area underneath the curve? Notice I miss a little bit. I'm missing here, 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 and so on. So how do I get closer and closer to the true area underneath the curve? What we have to do is we have to do two things to the rectangles. We have to make their widths smaller and smaller and smaller, which then means that we have to add more and more rectangles. If I do this process conceptually, I start to get more and more of this blue area here that I missed. I will in fact get the true area underneath the curve if I take all of those rectangles and I make them infinitesimally small in terms of their width. If I do, I then end up with the true area under the curve. That's the same thing as this, except we take a limit as the width of the rectangles approaches 0. That's written out in the following way. So the true area underneath the curve is this quantity here. Oops, summation. Height times width. This right here is the true area of the curve written out just more or less in a conceptual way. This quantity right here is referred to as the definite integral. However, it's at this point there's a change in notation. This quantity here, the true area underneath the curve, is rewritten. It's written in the following way. Now, here's what the various symbols mean. The summation symbol is replaced with this big squiggly s. This is called the integral sum. And then the numbers A and B on the graph above are written here and here, and they are given names. This is referred to as the lower limit of integration. It's the lesser number on the x-axis. This here is referred to as the upper limit of integration. It's the greater number on the x-axis. And this right here, the function itself, well, that's just the height of all of these rectangles. Height of all of these rectangles just describes the red function. That's this right here. This is referred to as the integrand, by the way. And then the rectangles being infinitesimal in terms of their widths, we've replaced the delta x with something that's infinitesimally small, dx. But this is still the sum of base times height between these 2 points. That's how you read what this statement is. And then at this point, once again, the theory comes into play. At this point in the calculus class, you get two things thrown at you. Something called the mean value theorem and something called Rolle's theorem. You would be wrestling with these theorems in class for literally a couple of weeks. And then you finally get to the punchline after all of that theory. And the punchline is how you evaluate a definite integral. The punchline is merely the following. In order to get the true area underneath the curve, what we actually have to find is another function. This other function turns out to be the reverse of finding a derivative. It's what's called the antiderivative. Once you find this function, then you plug into it these two numbers, and you subtract. When you do, you in fact get the true area underneath the curve. Writing this all out in terms of its symbols, it looks like this. Some of you know this, but I also know that some of you don't. Okay, now what is what here? Most of this stuff is just symbols. First of all, we have this new function referred to as capital F of x. Finding capital F of x, as you'll see, is the reverse of differentiation. It's called the antiderivative of the original function f of x. And then what we do is we take that new function once we find it, and as you'll see for polynomials, it's easy to do. And we then evaluate that function. That's what the vertical line means. The vertical line is just symbology. It means evaluate between. Evaluate between the value of b and the value of a. What you do with this new function is you plug into it first the value of b. That's this right here, and it gives you some number. And then you subtract from that what happens with the function when you plug the value of a. That gives you another number. The difference between the two is the true area underneath the curve. But in terms of the actual process itself, most of the process of integration is finding this function. For polynomials, it's easy. They quote to you what it is and how it works. As you write this down, notice this sort of looks a little backwards from what I did for derivatives. The power rule is it's called a little bit earlier. Okay, now why this quantity here? Well, this quantity here is the reverse of differentiation. It's called the antiderivative. What that means is that the derivative of this should be this. Watch this happen by using the rule from earlier. So from earlier, let me find the derivative of this. Remember what we do. Take the value of the exponent and bring it down in front. We take the value of the exponent and lower it by 1. And notice how it simplifies. Oops, next to me, I'm sorry. Notice how it simplifies. Boom, boom, like so. And then we end up with our original function. In other words, this quantity here is the reverse of differentiation. It's the antiderivative of this. That literally means that this guy's derivative is this. And that's what I just showed here. Now this process of finding the antiderivative of a polynomial works for just about anything except for this condition. If n is equal to -1, notice you end up with a 0 here in the denominator. You end up with another type of function called a natural logarithm. Don't worry, we don't have to worry about that in this class for quite a while. Okay? But for polynomials, evaluating the antiderivative is really easy to do, just using this as a process. So here's how it's done. So here's the second semester of calculus in 15 minutes. So you calculus is just one thing. And keeping it easy. Let's say you got a constant. So, now geometrically, let's say that I was going to find the area underneath the constant between 2 points. Let's just think of it like this. The constant, of course, is a horizontal line. So at a value of c, and let's just say that we look between 0 and 1. Notice that this is just a rectangle. What is the area of a rectangle? It's base times height. So notice that the base is just 1, and the height is c. So the area of this thing is just c. Now how do you show this as an integral? Very easily. Here's how you write it. So we're going from 0 to 1, and then we have the integrand, the function itself. In order to use that rule over there, think of this function as c times x to the 0th. Because what is x to the 0th? It's just 1 dx. This right here is notation. This right here is notation. You only work with this right here when finding the antiderivative. All that you do is take the exponent and increase it by 1. That's this right here. Let me get rid of this to dispel confusion. So you increase the value of the exponent by 1, and you divide by it. So, and then you evaluate between 0 and 1. Once again, all of this junk right here is just notation. Now what you do is you take 1 and plug it into this new function first. Subtract from that 0 plugged into this new function. And you just end up with c. Now that was easy to see here with some geometry. That's how you show it as the actual integral itself. Okay, what about a line? What about a function that's c times x? No, if it's a line, like so, with a slope of c. So I'll just write the function as cx. Let's say that I look at it between 0 and 1. Now right here, when x is equal to 1, by the way, this value on the line would be c times 1. It would just be c. Okay, right here is the area in question. It's just the area of a triangle. What is the geometrical formula for the area of a triangle? 1/2 base times height. So it's 1/2 times 1 times c. So the area here underneath the curve should just be 1/2 c. Let's see if it is by using the integral. So now we integrate from 0 to 1 cx. Think of this as x to the first power, just so you can see how this rule is employed. And then once again, this is notation, and this is notation. You only have to look at this right here. What we do is take the exponent and increase it by 1, and then divide by that new number, and then we evaluate between our 2 points. So 1. You stick 1 into this new function first, and you just get 1/2 c. And then you subtract the 0 plugged into the function second, minus 0. This ends up being 1/2 c, which once again we saw geometrically. And then lastly, for parabola, even a function as simple as a parabola, now this is where the ancient Greek tricks involved in geometry started to break down. For example. So if I just quickly sketched out the parabola here, once again we'll just go from 0 to 1 along the axis. Like so. Right here we'll say is 1. Right here is 0. Notice that we can't use some sort of simple geometry there to find the area underneath the curve. Literally the best the ancient Greeks could do was that process of the rectangles and only naked approximation. That was the best that the Greeks could do, even with something as relatively straightforward as this parabola. But now, using the definite integral through the theorems that I've skipped over, we can then very easily find the area underneath the curve. Here's then just as a process, how it's done. Once again, we're only concerned here with method. You're gonna get the theory and calculus class in. Now we go from 0 to 1, cx squared dx. Once again, you just worry about this piece of it right here. I take the value of the exponent and increase it by 1, and then divide by that new number. When you evaluate between 0 and 1. So you plug 1 to the function first, you just get 1/3 c, minus in this case 0 plugged into the function, which is once again 0, and then boom. There's our answer, 1/3 c. That's, I hate to say it, literally what you basically do in the second semester of the basic calculus. So give you the theory, blah, 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 and then you learn how to evaluate integrals in different functions. That's essentially the second semester. The worst thing about introductory calculus, however, even if it's high school calculus or AP calculus, is that in the first 2 semesters, which is all that you get in high school, you're never really told why it's so important. You're taught the theorems, you're taught the processes, you wrestle with the functions, and then boom, the year is over. So what? Well, you get the what and why it's so important actually in the 3rd semester of introductory calculus. The 3rd semester is called multivariable calculus. And that's truly where you see why calculus is so important as a process. A couple of times over the course of this class, a couple of times in the year, I'll give you a little bit of a taste of why it's so important, okay? Somebody had a hand up a moment ago.
I was just gonna ask why you do those.
Yeah, so what? So you learn basically technique in the first 2 semesters, how to do various functions, derivatives and integrals. And then you learn how to apply it in the 3rd semester, and that's where you really learn why it's so important. But unfortunately, that's just beyond the high school level. Okay? Let me pass on to you the file. Well, you'll notice that your calculus textbook, for example, at the end of the year this year, you're only going to be about 2/3 of the time. It's the remaining important parts. No, it doesn't. No. Even BC. Yeah, AB and BC are virtually the same thing. BC does one more topic, if I remember correctly, than AB does. In high school calculus, you get the gist of it, even without being in AP. But unfortunately, even AP calculus BC doesn't get the multivariate. It's always the third.
How about
They get a little bit more of a taste than I'm going to give you guys. They're going to see what's called a double integral. They're going to see a triple integral. You guys are going to give you a minor taste.
what's after what?
Then you start doing what's called differential integrals. Okay, take a look at this first of 2 handouts. This is on derivatives. The first 3 problems are to use the limit description of the derivative. That's the process that I did first. The next 3 problems, you could just go ahead and directly apply the shortcut. Now, all of these polynomials here are very simple and straightforward. You just literally go term by term in finding the derivative as you go. It does take a little bit of practice. As I said, I do expect everybody in honors physics to be able to find the derivatives of, say, these types of functions. And then similarly, get a taste of the multivariable that comes later with various shortcut methods that we use for, say, finding volumes and shapes. You're going to see something called the shell method, for example, a little bit later on in the class. The shell method is actually a simplified version of multivariable. So they do give you a little bit of a taste of it.
But it's not like
It's not the full blown. Okay, now take a look at this second handout for, once again, basic problems on integration. When it comes to the integration here, once again, you just go term by term. Take a look at numbers 2 and 3. In numbers 2 and 3, notice that you have two terms added together and there's parentheses surrounding it. When you apply the rule for integrating polynomials, you just go term by term. And you'll just end up with an expression, keep the parentheses around it, and then you plug in the limits of integration. Once again, all that we're concerned with here is technique. We're not concerned with the underlying theory. We don't care about that. It's just how do you evaluate these integrals. When you do the last integral, by the way, number 4, just be really careful there. The constant is the square root of 3. And then what would be the power of the exponent for the function there? On the x by itself, it would be x to the 1/2. So just be careful with that. Excuse me. Okay, so now, lastly, before I just turn you loose for the remainder of the period, in addition to these two handouts, which I will collect from you at the beginning of class on Friday, don't forget about this week's web assign, also due on Friday. This week's web assign, however, is just on free fall. All of those example problems are actually quite easy to do. If you're industrious, you could probably do both of these handouts in the next 10 minutes before the period ends. Those of you that already have some experience with calculus, if you're sitting next to somebody who doesn't understand the calculus because they haven't had it yet, go ahead and assist them, please. Okay. Chandler, that's good.